What if a robot could think on its own, not just follow commands but make decisions in real time, adapt to its surroundings, and even learn from its mistakes? Pi 0.5, equipped with 100 AI brains and a smart muscle system. This robot doesn't need Wi-Fi or preset maps to function. It can walk into a room, observe the situation, and start doing tasks like sorting dishes, just like a human would. Intrigued? Let's explore how this incredible technology works. The big idea. So, what's the secret behind this robot's brain? It's something called physical intelligence, or Pi 0.5. The big idea is surprisingly simple. Instead of having one central processor controlling everything, the robot's brains are spread out. Each part of the robot, its fingers, elbows, even its silicone skin, has its own mini brain. These small units, or Pi nodes, allow the robot to think and adjust instantly, without needing to check in with a central server. It's more like a team of quick-thinking muscles than a single command center. Imagine this. When this robot enters a room, it notices the dishes piling up in the sink and starts cleaning them without needing a map or Wi-Fi. It's a bit like how we humans do things. Seeing a problem, quickly reacting, and figuring out how to fix it without second guessing. What makes Pi 0.5 different? Pi 0.5 isn't just a single gadget or neural network. It's made up of two layers that tackle different problems, yet share the same name. The first layer is all about reflexes, like a robot's automatic reaction to its environment. The second layer gives the robot common sense, allowing it to understand more complex tasks. Let's break down how both work together to make this robot smarter and more capable. The lower layer, reflexes. Traditional robots operate by sending sensor readings back to one large central processor. That processor does a bunch of calculations, then sends commands to the robot's limbs. This works well in controlled environments like factories, where everything is predictable. But imagine trying to use that robot in your home. Cluttered rooms, moving obstacles, new layouts. This centralized system would struggle. It would take too long to process the information and use too much power. This is where the Pi 0.5 system shines. The lower layer of Pi 0.5, which focuses on reflexes, is designed to work faster and more efficiently. Each part of the robot, like its fingers or elbows, has its own mini processor, allowing it to act instantly. This decentralized system lets the robot react to its surroundings without needing to communicate with a central server, cutting down on delays and saving energy. In tests, this approach has shown impressive results. For example, when the robot uses a soft gripper, it can increase its accuracy by 30% and cut down on power consumption by 25% compared to traditional robots. This is a big deal when it comes to real-world tasks, like picking up fragile objects or performing long tasks without constantly recharging. The upper layer, common sense. But reflexes alone aren't enough for the robot to perform complex tasks. It also needs to understand what it's interacting with. For this, Pi 0.5 has an upper layer, which acts like the robot's brain, processing and understanding the environment. Think of it as the robot's common sense. This layer is based on a Vision Language Action Model, VLA. Essentially, it allows the robot to understand both visual data and language commands. It's trained to recognize objects, interpret language, and decide how to handle different situations. To make this work, Pi 0.5 was trained using a huge amount of diverse data. It learned from 400 hours of real-world footage, with robots navigating real homes and interacting with objects. This variety is key to its success. It didn't just learn how to operate in one type of environment, it learned how to adapt to new and unexpected situations. The upper layer's VLA system uses a combination of images, language, and task-specific data to teach the robot everything from basic object recognition to more complex tasks, like understanding how hard it should squeeze an object. For example, when asked to pick up a ceramic plate, the robot doesn't just grab it. It knows how to handle it gently, adjusting its grip as needed. How it learns. The way Pi 0.5 learns is both fascinating and effective. Rather than relying solely on scripted instructions or preset rules, Pi 0.5 learns from experience. It's like how we humans learn, by doing, not just memorizing. For instance, Pi 0.5 was trained in a variety of real-life scenarios. It spent hours watching robots perform tasks like cleaning homes, interacting with furniture, and picking up objects of various shapes and sizes. The robot was also trained using videos of simpler robots, helping it understand how to manipulate objects without a sophisticated setup. This broad exposure allows Pi 0.5 to function in many different environments, not just the ones it was originally trained in. In tests, Pi 0.5 showed impressive results. It could follow complex language instructions and successfully complete tasks 86% of the time, even when faced with new environments. When the test was made harder by introducing entirely new surroundings, the robot still performed well, with a success rate of 94%. These results show that Pi 0.5 doesn't just rely on memory. It can adapt and generalize, learning on the fly. Real-world testing. Now, let's see how Pi 0.5 performs in real-world conditions. The robot was put to the test in actual strangers' homes, with no prior setup or markers. The tasks included making the bed, folding laundry, cleaning up toys, and even wiping down tables. While the robot sometimes made mistakes, like misidentifying a plush toy or getting the arm trajectory wrong, it quickly corrected itself and continued with the task. This is where Pi 0.5's decentralized intelligence really comes into play. Even if one part of the robot gets interrupted or makes a mistake, the other parts can still continue. This allows the robot to recover quickly and get back on track. For instance, when a bystander accidentally bumped the robot while it was cleaning, Pi 0.5 didn't freak out. It just recalculated and kept wiping. This shows that the system is resilient and able to adapt in real time. It doesn't need to constantly check with a central brain, which is a huge advantage when it comes to performing tasks in dynamic, unpredictable environments. The future of Pi 0.5. So, what's next for Pi 0.5? While the robot is already impressively capable, the team behind it is working on ways to make it even smarter. One of the goals is to create robots that can learn entirely from their experiences, without needing human input. Imagine a robot that could watch its own performance and adjust accordingly, without needing to be reprogrammed each time. Another exciting possibility is transferring the robot's skills from one type of environment to another. This means a robot trained in one home could quickly adapt to work in a hospital, grocery store, or any other place. This ability to transfer skills across different environments is something that's never been possible before. In the future, Pi 0.5 could even learn from the things it does wrong, asking questions on the fly to improve its performance. The dream is to have robots that can perform in any setting, without the need for constant retraining. The ability to adapt, learn, and improve is the key to making robots more useful in everyday life. This is only the beginning, and the next steps are sure to be even more exciting. So, what real-world chore would you trust a Pi 0.5 powered robot to tackle first? Let us know in the comments, and don't forget to like and subscribe for more amazing insights into the world of AI.